Hello everyone and welcome to CSC Final Year Project Showcase. Our project is building a full task-oriented conversational agent in low-resource settings. Very specifically, solving the problem of how to implement a task-oriented conversational agent in low-resource settings, addressing the overfitting issue arise when optimizing dialog policy using reinforcement learning and utilizing pipeline ensembling in natural language understanding. Let's see the common architecture of a task-oriented conversational agent to better understand the problem. It contains 4 components. First, NLU or Natural Language Understanding component, which takes a natural language utterance and converts into a semantic form called Dialog Act. Second, Dialog State Tracker that maintains the state of the conversation. Third, Dialog Policy Learner that takes the next best action based on the state of the conversation. Fourth, Natural Language Generation component that converts this action into a bot utterance. When considering research on creating task-oriented conversational agent, building one in low-resource settings remains a challenge, especially utilizing data-hungry state-of-the-art approaches. When considering NLU, state-of-the-art is pipeline-based approaches. Although ensembling pipeline seems like a sound way to improve NLU performance, it has not been researched yet. In dialog policy optimization, state-of-the-art is reinforcement learning-based approaches. However, RL-based approaches requires a large dataset and tends to overfit in low-resource settings. Therefore, developing a full task-oriented conversational agent that uses RL-based dialog policy and ensemble NLU pipelines can be considered as a foremost step in low-resource research. Let's see how we approach the problem. When considering dialog policy optimization, we use 2 novel approaches. The first, a novel probability-based self-play technique. The second is a reward-based sampling technique that prioritizes failed dialogues over successful ones. Here, instead of directly using the training data for training, we use it to capture the data distribution. Then we add a small noise to reduce overfitting and increase exploration. Then we synthesize agendas and use the simulator to simulate and train the reinforcement learning-based agent. After some iterations of training, we use the reward function to capture the degree of success and failure and update the sampling distribution. The goal is to prioritize failed dialogues over successful ones. And the intuition is that the agent can learn more from the failed dialogues over successful ones. The probability-based self-play techniques, which we use, is used to address the overfitting issue, while the reward-based sampling technique is used to address the insufficient exploration of agenda space that can occur. We formulate these 2 equations for updating distributions based on the reward. In NLU, to improve the performance in both intent classification and entity extraction, we implemented novel pipeline ensembling technique. The ensembling algorithm used the confidence each pipeline generated for each intent or entity and a performance metric that indicate how good that pipeline is. We formulate the 2 equations for each of the 2 tasks. The equation in the left is for intent classification, while the equation in the right is for entity extraction. In NLU, to improve the performance in both intent classification and entity extraction, we implemented novel pipeline ensembling technique. The ensembling algorithm used the confidence each pipeline generated for each intent or entity and a performance metric that indicate how good that pipeline is. We formulate the 2 equations for each of the 2 tasks. The equation in the left is for intent classification, while the equation in the right is for entity extraction. Furthermore, we utilize the work we did on natural language understanding and dialog policy to create a full conversational agent. Here, we use a conversational data set and a data extractor to create data sets for each of the components: natural language understanding, dialog policy, as well as natural language generation. We ran several well-structured experiments to evaluate our methodology. If we consider dialog policy component, we ran 2 experiments to evaluate it. One to evaluate the approach against baseline, and the other is to measure the rate of convergence. We used the open source simulator described by Lee and others for both experiments. The experiment shows that our approach performs without overfitting, and the reward-based sampling further improves the agent by an average of 11.03%. The second experiment shows that for all RL algorithms we evaluated, there isn't any apparent lag between test and train success rate. We evaluate the pipeline ensembling method for both tasks, intent classification and entity extraction. To better evaluate the approach, we use different performance metrics. The evaluations indicate our pipeline ensembling approach achieves significant performance improvement. Especially, the best performing pipeline has achieved improvement of 4.4% in precision, 5.5% in recall, and 3.7% in F1 score, and 5.7% in accuracy in intent classification. In entity extraction, it has achieved an improvement of 17.2% in precision, 7.9% in F1 score, and 11.3% in accuracy. We ran human-based evaluation to evaluate the performance of our conversational agent. We used the conversational agent introduced in the paper titled End-to-End Task Completion Neural Dialog System as the baseline. As visualization depicts, our approach achieved a significant improvement over the baseline. In conclusion, we successfully addressed the overfitting issue arise when dialog policy is optimized using reinforcement learning-based approaches by using a probability-based self-play approach. We also introduced another reward-based sampling technique that improved the task completion rate even further. We also improved the performance of natural language understanding component by using a pipeline ensembling approach. We utilized this work to create a full conversational agent that outperformed the baseline significantly in human-based evaluation. We open sourced our research at AIVU under Apache 2.0 license, and we published a conference paper at 34th Pacific Asia Conference on Language Information and Computation, which is a B-grade conference under core ranking. We also submitted a journal article to the Computational Linguistics Journal, which has an impact factor of 2.510 and is a Scopus Index journal. Let's look at a demo. Thank you for your time.